Bam! Mr. Taru. Well, my wife and I have been preparing with our neighbors for the arrival of Hurricane Irma. Since we live in Florida, it is everything that is in the news. Now I can stare at the news for the next 48 hours and getting even more anxious about the arrival of this hurricane, which I think we're as ready as we can be for. Or we can come up with another free math video, and that's what we're going to do. Today we're going to be taking a look at the domain of rational functions. Our previous video, and this is going to be basically part 2 of a 3-part video series here, trying to respond to my pre-calculus students' struggle this year with finding the domain of functions. So we talked about combining square root functions and when is it appropriate to find the domain of those combined functions. It's basically always before you can simplify. Again, straight up domain of rational functions here. We're going to have a little bit of radicals thrown in, and our last example is going to involve kind of a precursor of what it's going to look like to find the domain of composite functions and decomposing functions. And in our third video coming up after this, we're going to be talking about pretty much the same idea, but we'll be combining these rational functions and pointing out really that you need to find that domain before you simplify, before you add those fractions or do the division or so on and so on. So our first of 3 examples here, we're going to find the domain of h of x where it's equal to 2 divided by x minus 3. Okay, the thing with pre-calculus, and you might just be using this for Algebra 1, but when you get into pre-calculus and these advanced mathematics, a lot of what you're learning is review. But they're putting all these different types of functions in at the same time. And at this early stage of our pre-calculus, we're only looking at rational functions and square roots, but we'll be talking about logarithms later on in the year, trig functions, so on and so on. You need to, when you're being asked to find what the domain is, basically, what numbers are you allowed to plug into these functions and to get a real solution. And you need to think about what you're looking at. When you're dividing, you can't divide by 0. When you're talking about square root symbols or even roots in general, you cannot even root a negative number. Well, those statements are what guide you on finding these domains. And don't fall into that idea, well, my teacher did a couple of problems and they kept making the denominator not equal to 0, so that must be how you find the domain for all of our functions. Well, no, that same rule does not apply again with even roots. It's different. You can't even root a negative number. So keep that in mind as you're doing these problems. Here we have a denominator of x minus 3. Well, you can't divide by 0. Now that doesn't mean that x can't be 0. It means that the entire, let's pick a different color here, the entire denominator of x minus 3 cannot equal 0. And that is your setup to find that domain. We're simply going to add both sides by 3 and get that x cannot equal to 3. Now your domain, if you are using sort of inequality notation for the domain, that is sufficient. If you're using interval notation, like I'm doing in my pre-calculus class, you're going to say that x can go from negative infinity to 3, or, that's that upside down u there, pick up on the other side of 3 and go from 3 to infinity. Now the one, oh, chalk down! Now the one nice thing about this interval notation is, the domain doesn't go from like 4, 5, 6, and 7 because we're restricting out or eliminating the actual value of 3. No, it's approaching 3. On a number line, you would be talking about a domain that goes from negative infinity and just has a tiny little hole right there at 3 and then picks back up. Every number, within the x-axis, any real value is going to be part of this domain. If you can plug anything in for x, 3.000001, and when you subtract by 3, the denominator is not 0, so that'll give you a real solution. Okay, so the domain's everything but equal to, cannot be equal to 3. Well, now down here, we have our denominator. Again, we have a rational function. We have division. You cannot divide by 0. Okay, that tells you how to, again, set up this, this process of finding what the domain is. X squared minus x minus 12 cannot equal to 0. And we're solving a quadratic equation here. So now we can solve this using the quadratic formula. We can solve this through the completing the square process, which actually is what derives the quadratic formula. Or we might remember our factoring skills. We have a quadratic, yeah, I've been up a long time, worrying about this hurricane and also doing a lot of work preparing for it, our leading coefficient for our quadratic is 1. So those are the easier quadratics to factor. And we're looking for factors of negative 12 that add to our middle coefficient of negative 1. So you got, positive, our last constant here is negative, so we need to have factors of different signs. So we can have 1 and negative 12, or negative 12 and 1, or 2 and negative 6, or negative 2 and positive 6, or we can have that pattern, or that, not pattern, but that pair of factors of, let's see, need our middle term to be negative, so we're going to have x minus 4 times x plus 3, and that is not equal to 0. So we set each of these kind of like we're solving by factoring, only we're looking for that sort of non-solution. We have x minus 4 cannot be 0, and x plus 3 cannot be 0. Adding 4 to both sides, we get x cannot be equal to 4. And subtracting both sides by 3, we have also that x cannot equal negative 3. And on the number line, or not on the number line, but with interval notation, that means that we'd be looking for negative infinity to 4. Oh, we should be going from low to high. So negative 3, or from negative 3 to positive 4, or from 4 to infinity and beyond. So this is what, eliminating a couple of values from our domain certainly is a little bit more efficient and easier to write with inequality notation, but that is what it looks like with interval notation. These round parentheses, if you've forgotten, means that you're not including those values. If, well, let's see, maybe we'll see it over here as far as how to write that domain. Now on our third example here, we're getting a little bit more complicated because not only do we have a rational function of fraction, which means division, but we have that even root, we have that square root. So we're going to have to do two things here. We're going to have to make sure that x minus 1, again, does not equal 0, but that's not going to be the only restriction that we have to worry about because, again, that square root in the numerator, we need to make sure that x plus 7 is greater than or equal to 0. Well, we can subtract both sides by 7 and get that x has to be greater than or equal to negative 7. And here we're going to just add both sides by 1 and get x cannot equal positive 1. Okay, now let's talk about this interval notation I'm using here of or. There's only one condition in this equation. X minus 3 cannot be equal to 0. So either this interval will work or this interval will work. Because, if I plug in something between negative infinity and 3 like 0, 0 minus 3 is negative 3. It's not 0, we get a real answer. If I pick something bigger than 3, which I see now I kind of said 2, but that should be a comma. Okay. Positive 3 to infinity. If I pick something like 4, and 4 minus 3 is 1, 2 divided by 1, real solution. Well, here we have two conditions in the same equation, not just one. So when we go to look at these inequalities, both of those conditions have to pass. You see, for the square root symbol, x has to be greater than or equal to negative 7. Well, on a number line, that looks like this. And there's our positive 1, our shading, at least for the square root that's in the numerator. That square root is going to give us a real solution as long as we plug in a number that is negative 7 or larger. Except when we get to 1. When you come in over here and you go, hey, wait a minute, we can't divide by 0. So while this green inequality graph is good for the square root, it's not good for the denominator. And I need to come up here and go, you know what? No, we need to eliminate from these values that satisfy this condition, we need to eliminate that value of 1. So both of these conditions must pass. And that's the and symbol for your inequality notation. Now, the shading along my number line is satisfying both of these conditions. Indeed, a number between negative 7 and positive 1 is both going to give us a positive value for this expression of x plus 7, and it's going to be any value that's not equal to 1. If it's equal to 1, of course, we're dividing by 0, and that's undefined. And same if we go to the right of 1, like at 2, 3, or 4, or so on. So I'm going to shift my inequality or my interval notation here and say that, okay, here's my shading that matches both of these conditions. So anything from -7 to 1, or, because there's stuff over here that works as well, once we get to the other side of 1 and go to infinity and beyond, we're going to have values that satisfy both of these conditions, and that is the end of our third example. I just got one coming up, one more left right now. For our last example, we have h of x is equal to 1 over 3 divided by x minus 1 minus 2. Now this last example it's quite interesting. And there's a lot of different ways I can take a look at this problem. First of all, I can just say, hey, what's the domain? We just talked about finding domain of rational functions, and let's just focus on the fact that you cannot divide by 0. We're going to do some color coding here. We have a fraction sort of in our fraction. We have a denominator of x minus 1, just x minus 1. And that denominator cannot be equal to 0. So x cannot be equal to 1. Of course, I'm doing that, finding that by adding both sides by 1. But we also, we don't have just one fraction bar in this, this equation. We've got two. Of course, this big old fraction bar right there. And so all of this, that 3 divided by x minus 1 minus 2 also cannot be equal to 0. So two fraction bars, sort of like a rational function inside of another rational function. Two fraction bars means two possibilities, potentially two times that the denominator or a denominator can be equal to 0. And you need to account for that entire denominator, whether it's just this little bit x minus 1 or this whole thing underneath the blue fraction bar. Those cannot be equal to 0. So how do we solve this? Hopefully you remember that you cannot solve for a variable when it's in the denominator. So we're going to add both sides by 2 to undo that subtraction. We're going to do the inverse math operation. So now we have 3 over x minus 1 cannot equal to positive 2. And there's a couple ways we can deal with this. Really, we have one fraction on the left, and we have one fraction on the right. And when you have an equation, it gets a little bit sketchy with inequalities. Not so much here with a not equal to sign, but what I'm going to say here might be a little bit sketchy if you have like a less than or equal than sign. You can flip both sides of the equation. But with inequalities, well, first of all, you can't do that when there's more than one fraction on either side of the equation, or both sides. It has to be one fraction on each side. But let's not get ourselves confused with any kind of rules about maybe having to flip the sign of the inequality or something like that, or the direction. Let's just say this variable of x is inside the math operation of division. So if I want to get it out of that math operation, I need to apply the inverse math operation, which of course is multiplication. So we're going to identify this entire denominator and multiply both sides of the inequality. I think I might have been saying equation earlier, but this is an inequality, to both sides. So x minus 1 divided by x minus 1 is just simply 1. So we have 3 is not equal to 2x minus, started to distribute that, doing a couple steps at once. Distribute that value of 2, and we get 3 cannot equal 2x minus 2. Add 2 to both sides to undo that subtraction. Divide both sides by 2, and we get x cannot equal 5/2. So because we have a fraction within a fraction, we end up with two restrictions on our domain. X cannot be equal to 1, and x cannot be equal to 5/2, because either one of these values will somewhere within this rational function create a denominator which is equal to 0. You can't divide by 0. Now notice I'm not saying anything about, we have to have a denominator or some expression that's greater than or equal to 0, because we don't have any even roots in this problem. Now, I don't know about your math books, but for my students, in pre-calculus, we've got combining functions and composition functions in the same section. So we're going to stretch this out a little bit, even though we already know what the domain is, every real number except 1 and 5/2. And let's talk a little bit about decomposition of functions. It does seem like there's, well, a function inside of another function. I mean, that's what we do with compositions like f of g and g of x. We take a function like f of g, we take the function g and put it into function f. I've got, well, actually I have a full playlist of pre-calculus videos, and I'll have a link to that in the description if you want any additional explanations, or if you want a big review of composition of functions. But it does seem like we have a 3 over x minus 1 inside of a bigger function. So you know what we can do? We can say, how about we let f equal this little piece here. And if we think about, that idea that a variable is just sort of an empty place to put something in, or it represents an unknown value, well, if we say that f of x is equal to 3 over x minus 1, then that expression must have had a variable, an open place to go into this equation. It's actually called an open sentence, these equations that have variables in them. So if I take the 3 over x minus 1 out and think, well, there must have been a variable for this expression to go into, then g of x could be possibly equal to, when you do a composition of functions, two people don't necessarily have to have the same two answers, as long as they composition together the same. But we could say that g of x is equal to 1 over, now I see this open space here, again, 3 over x minus 1. How about we let that be the variable of g and say it's x minus 2? Well, if g is 1 divided by something minus 2, and f is that 1 divided by something, f is that something that gets put in place of x minus 2, well then this is equal to g 1 something minus 2, 1 over something minus 2. Okay, same pattern. So the framework or the outside function is g. I said g. G. And function f is what that 3 over x minus 1 is what went in for that variable. Awesome. Okay. Now, another cautionary note about finding domain of composition of functions, and we'll be done with this lesson. Be careful that when you find a composition of functions, what you do is you find the domain of what will be that inside function, the domain of, in this case, the 3 over x minus 1, and then you find the domain of the overall composition. That's the 1 over 3 divided by x minus 1 minus 2. Here's what's going to happen if you do your composition of functions and then simplify before you go to find the domain. If I go to simplify this, we need common denominators, including that 2 over 1. We have a denominator of x minus 1 and a denominator of 1. So let's do some work to make that common denominator show up. Now I'm going to write, I'm finding common denominators so I can subtract or subtract these two fractions together. So I'm just going to write the x minus 1 as our common denominator. Distribute the negative 2. Add like terms. And now we have a single, sort of like a single term or a fraction, if you will, in the numerator, because this is kind of like 1 over 1, and we have a fraction in the denominator. So we can remember that this main fraction bar is a division symbol. We have 1 divided by our denominator. Well, remember when you learned how to divide fractions, you multiplied by the reciprocal of the second fraction. Well, that second fraction is our denominator. So we're going to do my little pigtail notation up here, change this division to multiplication, and multiply by the reciprocal of the denominator, multiply by the reciprocal of that second fraction. Now hopefully I'm not skipping a little bit, a few too many steps here, but again, I'm changing this division, 1 divided by this fraction, to 1 times the reciprocal of that second fraction. So I'm not really canceling out this denominator. I'm flipping this up and changing the division to multiplication. I'm just skipping this step as far as in written terms, because I don't like to work my way up. It's kind of weird to look up through your steps of work. I'm just kind of running out of room here. Well, of course, and then 1 times anything is anything. It's whatever you started with. So we have h of x is equal to x minus 1 over negative 2x plus 5. If I look at this sort of basically composition function and go to find the domain after I simplify, the only thing in a denominator is the negative 2x plus 5. And if I go to find a restriction on that domain, say negative 2x plus 5 cannot equal 0, well, if I add both sides by 2x, you see what's happening here? We have 5 cannot equal 2x, we have 5 cannot equal 2x. I'm going to get sort of a partial answer to the restriction on the domain, but through the simplification process, have lost the fact that in the original problem, we had a denominator of x minus 1 and a whole denominator of 3 over x minus 1 minus 2. So when you do your composition of functions, and indeed when you add, subtract, multiply, and divide, especially with your rational functions, make sure you find that domain before you go to simplify. I'm Mr. True. Bam! Oh, and by the way, if you get to see a video in a couple of days, we've had no real damage here from Hurricane Irma with all of our preparation, and if you don't see video for a couple of weeks, hopefully not, but we'll probably we'll be doing some repairs in the house before I can make another math lesson. Again, I'm Mr. True. Go do your homework.